Modern processors are designed to do more work in less time. One of the most powerful techniques that makes this possible is vectorization, processing multiple pieces of data at the same time instead of one by one. But as software grows more complex, fixed-size vectors start to become a limitation. In traditional ARM architectures, vectorization is handled using Neon. Neon vector registers are always 128 bits wide. That size never changes regardless of the processor. This means programmers must write code that explicitly fits that fixed width. With ARM version 8.2, a new approach is introduced, a scalable vector extension, also known as SVE. Unlike Neon, SVE vector registers do not have a fixed size. Instead, their length depends on the hardware implementation. An SVE vector can be as small as 128 bits or as large as 2048 bits, always in multiples of 128 bits. The key benefit of SVE is scalability. Programmers no longer need to know or care about the exact vector length. The same program can run correctly and efficiently on different processors, even those processors use different vector sizes. This makes SVE forward scalable. SVE introduces its own set of registers alongside Neon. There are 32 Z registers named Z0 through Z31, which holds data. There are also predicate registers named P0 through P15, as well as special registers called FFR. Predicate registers are bit masks. Each bit in a predicate register corresponds to one lane in a vector. If a bit is set to 1, the lane is active. If it's set to 0, the lane is disabled. This mechanism replaces the loop reminder handling that was required in Neon. Operations in SVE include a predicate register to control which lanes participate. For example, add Z1 to Z2 store the result in Z0, but only for the lanes enabled by predicate register P0. Inactive lanes remain unchanged. Building on SVE, ARM version 9 introduces another extension, the Scalable Matrix Extension or SME. While SVE operates on one-dimensional vectors, SME adds architectural support for two-dimensional matrix operations. This makes it possible to efficiently multiply, accumulate, and transform large data matrices directly in hardware. These capabilities are especially useful for workloads such as machine learning, signal processing, graphics, and scientific computing. Like SVE, SME is also scalable and adapts to hardware it runs on. However, not every processor supports these extensions. For example, the Raspberry Pi 5 uses an ARM v8.2 core, which does not include the scalable vector extension. Even so, understanding SVE and SME is important. They represent the direction ARM architectures are heading towards increasingly scalable and hardware-accelerated computation. Today, we scale vectors and matrices. In future, hardware may handle even higher dimensional data structures. Vectorization is no longer just an optimization technique. It's a foundation for what comes next.